How's it going, ladies and gentlemen? Mr. Donahue here. Once again, this time we're going to take a look at 5.3 and 4 problems that are going to look at enthalpy and enthalpies of reaction. All right, so let's take a look at number 8. Number 8 says explain what the sign of delta H is for endothermic and for exothermic reactions. So if it's endothermic is saying that it is absorbing energy. So we're going to have a positive delta H value because it's gaining energy, right? And then if it's exothermic, think of exoskeletons. Exo means on the outside, so exothermic means that energy is moving to the outside. It's losing enthalpy, so it's a negative delta H. It's losing stuff. So there's less enthalpy at the end than there was at the beginning. So generally endothermic processes get colder because it's absorbing energy from its surroundings. So these things tend to get cold, and exothermic things tend to get hot because they're releasing energy. So if you're doing a reaction and the temperature goes up, it's an exothermic reaction. And if you're doing an experiment and the temperature goes down for the stuff, it's endothermic, it's absorbing that heat. All right, 9. Which of the following statements is or are false? So these problems always frustrate me because it's like I'm trying to find the wrong answer and then my brain gets confused when I find a correct statement. So what I do for these ones is I draw a little smiley face. If it's a true statement, I give it a smiley face. If it's a frown, then it's a false statement. And then I go back and go, all right, what are they asking again? So for this one, it says internal energy is a state function. That is true. That is true. So I'm going to give it a smiley face because it doesn't matter how you got there. It just matters what state you're in. That's the internal energy. Next one says enthalpy is an intensive property, which is not a true statement. If you have more stuff, you got more enthalpy. Okay. 3, it says the enthalpy change for a reaction is equal in magnitude but opposite in sign to the enthalpy change for the reverse reaction. So they're saying if you went from A to B and there was a delta H, if you did the opposite from B to A, it's going to be the same number but just opposite in sign. And that is a true statement, so I'm going to give it a smiley face. 4 says the enthalpy change for a reaction depends on the state of the reactants and the products. That is also a very true statement, because if I'm talking about, A to B, if A is a solid versus A starting as a gas, you're going to have different delta H's. The delta H values are going to be different, right? So it does depend on what they start at. And the last one, the enthalpy of a reaction is equal to the heat of the reaction. Yeah, that's just how we use words to describe things. So 9, again, it says which of the following statements is or are false. The only one that's false would be choice 2, so it's going to be, boom, B, right? That's the letter B. All right, number 10. The following reaction can be described as what? So we have this reaction, and then it tells us our delta H is a positive value of that much. So the positive delta H tells me that it's gaining heat, so it's going to be endothermic, right? So endothermic with energy being released, nope, that release part makes it wrong. Endothermic with energy being absorbed, sure looks like that's going to be our answer, but let's look at the rest of them. Exothermic, nope, with energy being released. That's true for exothermic reactions, but that's not what's happening here. Exothermic with energy being absorbed, nope, but it is being absorbed, but it's not exothermic. Thermoneutral, which means the delta H would be like 0 because it'd be neutral, and that is not true because we have a value for delta H. So choice B, final answer. 11, a negative delta H process corresponds to what kind of process? An exothermic. All right, you need to commit this to memory. Negative delta H, exothermic. Delta H for an endothermic process is, again, you got to commit this to memory, positive. It's a positive delta H, it's endothermic. If it is an exothermic process, then it needs to be a negative delta H, it's losing heat. 13, here we're going to do a little bit of math. It says the value of delta H naught for the following reactions is 790 kilojoules. So that's telling me that the delta H is 790 kilojoules. What is the enthalpy change when 2.6 grams of sulfur reacts? All right, well, what we're going to want to do right now is take a look at this. We're going to set up a proportion. We're looking at sulfur, so I know that 2 is for moles. So if I have 2 moles of sulfur reacting, it's going to give off 700, or it's going to absorb 790 kilojoules. So now they're saying, well, what if I use just 2.6 grams? So to figure that out, I got to convert the grams to moles. So I go, all right, well, sulfur has a atomic mass of 32.07. So if I want to get moles, it's going to be grams over the GFM. So I'm going to get 2.6 over that 32.07, and I'm going to get 0.08107 moles of sulfur. So now I can set up a proportion. I know for every 2 moles of sulfur, there's 790 kilojoules involved, but this time I only have 0.08107 moles of sulfur. How much kilojoules would that be? So now we can cross multiply and divide, and I get X to equal a 32.0 kilojoules. And I just noticed something. This is a negative sign that goes with the 790, so it should be negative 790. So this is going to be negative 32.0, right? Because that would have been negative. Oops, my bad. Hate me. I'm sorry. All right, 14 says the value of delta H naught for the following reactions is, again, that's a negative sign. Call it my mistake. Oops. Negative 6535 kilojoules. How much energy is released when 32 grams of C6H6 liquid combusts? So again, this is telling me that my delta H is equal to negative 6535 kilojoules. And the thing that I'm interested in is my C6H6. So again, it's, hey, set up a proportion for every 2 moles of C6H6, I release 6535 kilojoules. Right, so that's 2 moles, but they tell me grams. So again, I have to convert between grams to moles. So I got to look up and figure out the gram volume mass for C6H6. So I'm going to do that. I got to look up carbon, so it's going to be 6 times 12.01 plus 6 H's, so 6 times 1.01, and then I'm going to add all those together, and I get a mass of 78.12 grams per mole. So now I need to get moles. If I'm using 32 grams, I got to do grams divided by the GFM, because that's going to give me my moles. So now I plug and chug 32.00 grams divided by 78.12 grams per mole, and I end up with 0.4096 moles of C6H6. So that I'm going to put under this proportion right here. 0.4096 is to X. So now I can cross multiply and divide, and I get X to equal negative 1338 kilojoules as my final answer. All right. 15. More of the same but different. Hydrogen peroxide decomposes to water and oxygen at a constant pressure. They're represented by the reaction as follows. They give you the delta H. It says calculate Q, which is, again, like kilojoules, when 12.50 grams of hydrogen peroxide decomposes. So again, we're going to set up a proportion. I know that it's a 2 moles of hydrogen peroxide gives me negative 196 kilojoules as my delta H. So now I got to set up a proportion. Well, how many moles is 12.5 grams of hydrogen peroxide? So I got to look up, well, if I'm doing H2O2, its mass is going to be 2 times that of a hydrogen, which is 1.01, and 2 times the mass of the oxygen, which is 16.00. So I get a total mass of 34.02 grams per mole. So now if I want moles, I got to do grams divided by the GFM. So I get 12.50 grams divided by 34.02 grams per mole. And I get how many moles? 0.3674 moles. And then how much kilojoules would I get? Again, cross multiply and divide, and I get X to equal negative 36.01 kilojoules as my final answer for that one. And last one, which is a little bit more of the same but different, right? So it says the delta H naught for the following reaction is negative 482 kilojoules. How much heat is released to the surroundings when 13.45 grams of carbon monoxide, CO, gas completely combusts? So again, this is saying the delta H is equal to negative 482 kilojoules. And coincidentally, again, the object of interest is carbon monoxide, and it has a 2 coefficient, so it's a 2 to negative 482 kilojoules, Remember that 2 is coming from the coefficient. So 2 moles of the carbon monoxide releases 482 kilojoules. So we got to figure out how many moles of carbon monoxide do I have. So again, carbon is 12.01 and oxygen is 16.00. So when I get a formula mass, it's going to be 28.01 grams per mole. If I want moles, I'm going to have to do grams divided by that gram formula mass. So 13.45 divided by 28.01 grams per mole in grams. So I end up with 0.4802. So 0.4802 moles. So I plug that in up here. 0.4802 moles gives me X, cross multiply like we've been doing and divide, and I get X to equal -116 kilojoules. All right, cool. And that's it for this section. I hope you found it helpful. See you in class. Okay, bye.